Hi, this is Gary Rubenstein. This is the fourth part of a series of videos that takes you through what I consider to be sort of the big picture from kindergarten all the way through 12th grade math. And I'm up to part 4. The first 3 parts were about kindergarten through maybe 3rd grade, basic skills of adding, subtracting, multiplying, and dividing. And if I didn't make it clear enough, because I got some feedback on the first 3 videos, I definitely think that kids should memorize the times tables. That's sort of the goal. Yes, I taught some tricks, like if you know 5 times 4, but you don't know 5 times 5, you could do 5 times 4 and then add another 5. I think that a student who can't do that is a student who just memorizes 5 times 5 and has no idea of the relationship between the numbers on the times table is not going to go so far in math. So it's good to understand, but it also is necessary to have memorized the times table facts. And there's not many of them. There's maybe 30 that are like difficult for people, and a lot of the other ones are just real easy for people. And the same thing with adding. You know, you should know 8 plus 5 is 13, and you don't need to have like fancy tricks for it. But when I showed some methods of understanding like why 8 plus 5 is 13, I was just showing you some ways that help some people to think about it rather than just like a memorized fact. You know, it's not like saying 8 plus 5 is 13 and someone says, well, I memorized that. You know, that's not like memorizing, you know, bleep plus blort equals block. You know, it's, you know, a meaning, 3 meaningless words. 8 plus 5 equals 13 has a meaning behind it, and understanding the meaning is better than just memorizing 3 things as if they're just random words that have no meaning whatsoever. So after adding, subtracting, multiplying, and dividing, 2 big math concepts that come up are fractions and decimals, and I want to say some things about them. First of all, both of those things students and children get a feel for at an early age because, for instance, like the word half, you know, you could say you could have half that cookie. So I think kids at least have the idea of half, which kind of is a big deal because it's not a whole cookie, it's a half a cookie, and the idea that, and even when kids are like sharing something and one kid doesn't split the thing evenly, let's say there's a cookie and you're supposed to split it half and half, and one kid, you know, let's say it's one of those big cookies and they cut it, you know, like that, and this kid is like upset. Well, why are they upset? Because it was in half. So they even have a concept of that something's less than half. You know, do they know that this is a fifth of a cookie or a fourth? No, but they have the idea of a half, and it's good to in education to build off things that people know. So half is a starting point. Certainly, kids have seen pizzas that are often cut into 8 slices. They don't know that each one is an eighth, but they would recognize there's like a difference between a pizza that's cut like this and a pizza that's cut like that. As far as decimals go, well, in money, you know, when they see like 0.01, they might learn that that's like a penny, and 0.02 is 2 cents. And 100 is a dollar. So this idea that the numbers here, this 1 does not represent a dollar, it only represents a penny, whereas this one represents a dollar, and the idea that the place values, when there's this mysterious dot, have some kind of meaning to them. So let me spend some time on fractions. And a lot of these things are ways of teaching things that have been around for hundreds of years. So it's not like this is, I'm going to give you this, you know, such groundbreaking things. Actually, some of the modern things that I'm seeing about how to teach fractions, I don't like so much. So those people who are worried that my videos haven't been old school enough might like the idea that when we see a half, it's half of something, like half of a circle is a half, or half of a square could be half, or you could have some kind of rectangle, and you could have half shaded that way, or the same rectangle, we can shade half that way. So something that's kind of interesting to think about is that if you have a big circle and a small circle, this half, these are both halves, but they're halves of different things, which is like a little bit confusing, but it's something worth like thinking about. Like, are these things equivalent just because they're both half? And no, would you rather have half of the big cookie or half of the small cookie? Now, when you start cutting things into different amounts of equal pieces, for instance, when you cut the pizza that way, well, those are fourths. And I personally like the circles for illustrating fractions, although it is good to throw in some other shapes. Some shapes would be really hard to split into thirds, like rectangles and circles are the easiest things to split into fractions. You know, there are other things, like you could take a triangle and cut it into three equal pieces that way. But it would be really hard to cut that triangle, that same triangle, into 5 equal pieces. So usually you see rectangles and circles as the main things, because you could really see and agree that because all the pieces have to be equal to each other. You can't take something like this and split it up into different sizes and say that these are each fourths, because to be fourths, they all have to be equal to each other. When we kids split the cookie, they say, oh, you gave me the bigger half, or you gave yourself the bigger half, but then it's actually not a half. There's no such thing as the bigger half. If it's half, it's equal to the other half. A good thing to think about mathematically is comparing fractions. You know, like what's bigger, 1/2 or 1/4? And that comes down to, if I have 2 pizzas, and the pizzas are the same sized pizza, but one of them's cut into halves, one of them's cut into fourths, well, 1/2 is greater than 1/4. And in general, the bigger the denominator, the smaller the fraction. Notice how all my fractions so far are fractions that have 1 on top, called unit fractions. Those are good. We are going to get other numerators, but it is good to like concentrate on fractions that have 1 on top to give you a feel for the different things. Now we can also have something like this, where the number of slices is the denominator, and the number of things shaded is the numerator. So you could have numerators other than 1. So something like 3/4. And I do think that it's fun to like draw a picture and say, shade 5/8. And we go something like that, cut it into eighths, and shade just 5 of them. Now, once you start having, see, before we only had 1 in the numerator, so it was real easy. Although, by the way, it is interesting, even in this, to say, what if I have like a small pizza and a large pizza? Is it possible that 1/2 of this pizza could be less than 1/4 of that pizza? And that's kind of an interesting thing to think about. And yes, it is possible that even though this is 1/4, it could be bigger. But that doesn't mean that 1/4 is bigger than 1/2. It means that like 1/4 of the big pizza is bigger than 1/2 of the small pizza. But that's not a comparison of 1/4 and 1/2. That's a fourth of something. It's kind of like a fourth times multiplied by a large number can be bigger than a half multiplied by a smaller. Just something to think about. I just think it's like a thought-provoking. When I teach math, I like to pose what I call, in my mind, thought-provoking questions like, under what circumstance could 1/2 be less than 1/4? Well, it's never less than 1/4, but if it's 1/2 of a small thing versus 1/4 of a big thing, in that case, the half of that small thing could be smaller than the fourth of the large thing. Once you get numerators other than 1, you start being able to like compare things, like what's bigger, 3/4 or 5/8. And it's hard to compare those fractions sometimes. Like if we draw out a picture of 3/4 and a picture of 5/8, we can see that 3/4 does seem it's more of the pizza, because if I threw in this green slice, that would be somehow equal to 3/4. So it's interesting, like the idea of comparing two fractions that have different denominators by maybe drawing a picture of them. When I think about comparing fractions, I think the first comparison is always comparing to 1/2. Remember earlier I mentioned that the idea of half, like half a cookie, is something that kids learn at a pretty early age. You know, you only ate half your dinner, we say it's a vocabulary word. So comparing something to 1/2 is a good skill, because it could give us the idea that here's a half, and 5/8, the idea that, 5/8, well, 4/8 would be 1/2, and the extra eighth would be bigger, so 5/8 is actually bigger than a half. And maybe with enough examples like this, let's say I'm comparing 4/10 versus 1/2, and maybe students could get the idea of equivalent fractions, like, 5/10 would be 1/2, but this is only 4/10. So 4/10. But it's sometimes pretty difficult to compare two fractions with different denominators. But comparing to half might be something that students get a feel for. It's interesting to me when there's like a odd number in the denominator, like 3/5 versus 1/2. It's pretty hard to think about because fifths aren't like so easy to draw. And there's also this complicated idea of like fifths, so you can't actually do perfect half with fifths if I'm using like, a whole number of slices. So like 2/5 is a little bit less than a half, but 3/5 is a little bit more than a half. And this would be a good example where like drawing the picture might, but it could get really hard. Like if I want to know, 4/7 versus like 6/11. They're both bigger than a half, and it's hard to see. But that would be like an interesting question just to like have students mess around with. But to be able to compare fractions, well, we would need the concept of equivalent fractions. And the way equivalent fractions work is if I have something like 2/3 and I imagine it like that. If I were to take this pizza and take each slice, the green ones, this time it's green and red, it's tomato and peppers. And if I take this pizza and say, I actually have more than 3 people, so I wanted to make it into a different denominator, well, I can take each slice and cut it up into 2 pieces. So now the total number of pieces is 6, it doubled, whereas the number of green slices has doubled also to 4. So 2/3 and 4/6 are equivalent fractions. if I go back to my 2/3 picture, and if instead of cutting each piece into 2 slices, I cut each piece into 3 slices, now what happens is I have 9 slices altogether. The number of slices has tripled, but the number of green slices has tripled also. So these are all equivalent fractions. Maybe we get the idea that if you multiply the top and bottom by the same number, like if I multiply top and bottom by 5, I get another equivalent fraction. Notice how this denominator ends up being a multiple of 3. So I can't turn 2/3 into fifths very easily, but I could turn it into 6 or ninths or 12ths by multiplying both by 4. Because when I multiply both by 4, it's like I'm taking the whole pizza and taking each slice and cutting it up into 4 slices. Or multiply both by 5, or multiply both by 6, or multiply both by 7. I won't keep going with it. So I can get equivalent fractions by multiplying the numerator and denominator by the same number. Now you can sometimes do what's called reducing fractions. Reducing fractions is when I start with something like 4/6. And sometimes you can't really reduce a fraction very easily. So I'm starting with 4/6. And in this case, I'll make this red, and these are green. Yes, I can turn 4/6 into 8/12, but I'd rather get a reduced fraction, meaning what if I were to take something like glue and to somehow make the total number of slices smaller? I can make the total number of slices smaller by like fusing 2 pieces together. So these 2 pieces become one big piece, and these 2 pieces become one big piece, and these 2 pieces become one big piece. And if I fuse 2 pieces together, well, now what's happened is that it's now turned into 2/3. Mathematically speaking, I turned each 2 pieces into one piece, which is a form of division. Like 6 divided by 2 is 3, and 4 divided by 2 is 2. So we can always make equivalent fractions by multiplying the numerator and denominator by the same number. I could pick a number and just multiply top and bottom by it. But reducing is a little harder because whereas I can multiply top and bottom by anything I want, I can only divide top and bottom by a number that goes into both 4 and 6. And that's called reducing fractions. And sometimes you can reduce the fractions. Like if I have something like 5/6, I'm not able to reduce it. See, I can fuse pieces together, but the problem is there's only one green slice, so I can't fuse it together with another green slice. So this can't be reduced, and we can see that because 5 and 6 have what's called no, common factors. Whereas 4/6, we can divide both by 2. And this idea of like common factors, is there a number that goes into it? It's a pretty sophisticated idea, but it is something that kids can know, like, what are all the factors of 5, what are all the factors of 6, and we call it, by the way, when you have something like 4 and 6, and that 2 is like a factor, because the factors of 4 are 1, 2, and 4, the factors of 6 are 1, 2, 3, and 6, and the number 2. So we say 2 is what's called the greatest common factor. Abbreviated as GCF. Sometimes it's called, in higher math, it's called the greatest common divisor, which is GCD. But the idea of greatest common divisor is its own skill. You know, GCD of 6, 6 and 10 is 2, but the GCD of 6, let's just say of 8 and 12 is 4. The GCD, the thing that goes into both numbers, is the thing that you would divide by when you were reducing the fraction. And sometimes you have like something like 10 over 30, and you divide both by 5, let's say, and then you notice that you could divide both by 2. This is called lowest terms. Lowest terms is when the numerator and denominator don't have a common factor anymore. It's good to reduce things to lowest terms. You know, they're easier to visualize when they're reduced to lowest terms. So that's just some stuff about fractions. Actually, I'm going to keep going with fractions. If you want to compare two fractions, like 2/3 versus 3/5, it may be hard because they're both bigger than a half, so it might be hard to like tell, you know, which one is bigger. So the trick is, if they had the same denominator, you could compare them a lot more easily. Well, you can turn this denominator into a bigger number just by picking a bigger number and multiplying both 2 and 3 by that number. Well, if I choose to multiply them by the other denominator, it becomes 10 over 15, which is equal to 2/3. But I could do the same trick on this side. I could turn this 5 into any multiple of 5 by multiplying. So if I choose the other denominator, in this case 3, I get 9 over 15. So it turns out 2/3 is a little bit bigger than 3/5. This is like a good question. Like I would give that to students to like see. There's like manipulatives where you actually get to, you have these little like pizza pie shape Trivial Pursuit looking things, and you could actually, you know, put them on top of each other and see which one's bigger. This isn't well drawn. So that's comparing fractions with what's called common denominators. By getting the denominator to be the same number, which you could easily do by multiplying these numbers by this and these numbers by that, then you can compare them more easily. Common denominators are also used in adding. So if I want to add like 1/3 plus 1/4, just like if I'm comparing the fractions, it's better if they have common denominators. In this case, if I multiply 3 times 4, I get 12. That's a good common denominator because you could turn 1/3 into 12ths by multiplying top and bottom by 4. You could turn 1/4 into 12ths by multiplying top and bottom by 3. Then we could add those together. And subtraction works that way also. And fractions are a big thing. Students spend like months on them. I'm just spending a few minutes now giving you some of the basics behind fractions. Nowadays, I see, this is like a little, someone's going to watch this video and think I'm advocating for this, but the new like thing that I hear people talking about a lot is that fractions should not be visualized as pieces of a pie or a pizza, but instead, and maybe that's because, you know, you could have a big pizza and a half of a small pizza could be less than a fourth of a big pizza. I'm not sure. I mean, I guess that's what they're saying, but they actually want to put the fraction onto a number line. This isn't like so bad because, of course, with like a ruler, you measure and you have halves and fourths. I don't have a problem with that. Like give kids a ruler that has a fourth, a half, and 3/4. I do like that. But I guess the thing they're saying nowadays is that like 1/2 is like a position on the number line, and 1/4 is a position on the number line, and 1/3 is somewhere over there. And that kind of gets around the whole idea that you could have a small half and a large fourth. It's pretty sophisticated. I think that students can get the idea that half of a thing is bigger than a quarter of that same thing. And that when we're talking about a half is bigger than a quarter, we're talking about of the same object. So I'm not that like impressed with the whole like this number line idea is one that is, I think, a little too sophisticated. I mean, again, the ruler with half and a quarter on it and 3/4, that's fine. But like this like high level idea about how it's better to think of it as a point on a number line than it is to think of a pizza. No, pizza and pi is a great way to think about fractions. I'm seeing already that it was a little ambitious to think that in 40 minutes I was going to cover fractions and decimals. So I'm gonna change this to just say fractions, if you don't mind. Decimals will be the next video. So even though fractions generally means a thing that's broken up into pieces, and I'm taking certain number of pieces, you can have an idea like 5/4, the numerator. Numerator is bigger than the denominator. When that happens, we call this an improper fraction. When fractions were first invented, like things like 1/3, and 2/5, not first invented, but like in like the 1700s, when they taught them, they would call these types of fractions called vulgar fractions versus decimal fractions, which were what we now think of as decimals. Kind of funny, vulgar. Anyway, 5/4, that's where we're cutting a pizza into 4 slices, but we have 5 of them? How could you have more than 4 slices in a 4-slice pizza? Well, 5/4 is a number actually that's between 1 and 2. So there's 5/4. So 5/4 we say is equivalent to 1 plus 1/4, which we write as just 1 and 1/4. So there's nothing in between there. It's kind of funny because in math, a lot of times when there's nothing between two things, it means multiply. But in this case, the nothing between two things means that they're being added together. Standard way of converting improper fractions into what are called mixed numbers is to divide, and the remainder ends up being the numerator, and this quotient ends up being the whole number. I think turning improper fractions or going the other direction, like 2 and 3/4, I think this is a good, oops, I made a small circle, but the idea that 2 and 3/4 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 fourths. They can do that by drawing and counting, but the official way that you could also do that question is you multiply 4 times 2 to get 8. That's these 2 pizzas, and then you add on. So you do 2 times 4, and then you add on the 3, because that's the extra 3 slices. So 2 times 4 is 8. That's these 8 slices, plus the 3 that haven't been counted yet is 11 fourths. You can go in the other direction also. So those are mixed numbers, improper fractions. Sometimes when you're adding two fractions together, they want to know what's like 2/3 plus 3/5. And if you turn them into common denominators, remember before we compare them, you end up with 19 over 15, which is one whole, but then there's 4 slices or 4 left over. So they add. Subtracting mixed numbers is something that students struggle with a lot. You say something like 5 1/3 minus 1 1/2. Let me start by doing 5 1/2 minus 1 1/3, which is an easier question. The half and the third we turn into sixths, because 2 times 3 is 6. And then we could subtract 3 6 minus 2 6 is 1 6, and 5 minus 1 is 4. So that's the easy kind. But when I try the same thing with subtracting, we might whoops, this one's 2 6, that's 3 6. When I try the same thing with subtracting, I'll just cross these out, we run into a little problem because you can't do 2 6 minus 3 6. This is one of the hardest things of elementary school math, I would say. A lot of students just write 1 6 anyway. Remember this, 52 minus 13? And you couldn't do 2 minus 3, so you traded a 5 for 10 ones, and this became 12 minus 13, which is 9. Same idea here. We trade in the 5. We don't turn this 2 into a 12. We turn in the 5 for 6 6, and we already had 2 6. So this numerator does not become 12, but becomes 8. And now you can do 8 minus 3 and get 5 6. I would say that this is the hardest thing in math so far for students, subtracting. Some people build up to this with things like time and feet and inches. What were these numbers again? 5, 52, 13. So, 5 feet, 2 inches, and 1 3 minus 1 foot, 3 inches. So when you subtract, this becomes 4 feet. But this 2 doesn't become 12, it becomes 14, because I've traded a foot for 12 inches. Anyway, that concept of borrowing and not sticking a little 1 here like you do in this situation, but it's pretty hard. I definitely recommend visuals to explain, these different things. But I'm just going through, especially for parents who haven't seen math in a long time, certainly haven't. In real life, you never have to subtract fractions like this. Now multiplying, I think I would start by just multiplying like a whole number times a fraction. Because 5 times 1/10 is the same thing as 1/10 plus 1/10 plus 1/10 plus 1/10 plus 1/10, which is 5/10. Well, you might notice that you would get that same answer if you multiplied the numerator 5 times 1 and just left the denominator alone. And that is how you multiply a whole number times a fraction. So 3 times 2/8 will be 6/8. It's not so much a memory. Hopefully it's a thing that students can get a feel for because they know that 3 times is the same thing as adding the 3 things together. But it doesn't become 24 on the bottom because I'm adding eighths together. When you add eighths together, you get eighths. I should mention, when students add fractions, they are sometimes tempted to add the denominators together. But just like if I have 2 dogs plus 2 dogs plus 2 dogs, and I get 6 dogs, 2/8 plus 2/8 plus 2/8 is 6/8. It's not 6/24. But that is something that's like not crazy for someone to write, to think that you could add. Remember, I haven't done. I went through adding pretty fast here. So why don't I just mention that the answer is not 2/7. It's too bad it's not 2/7. It just isn't true. If they drew it out, if they actually drew 1/3 and 1/4 and 2/7, they would see it's hard to draw sevenths, but they just don't. It just doesn't work, unfortunately. So it actually becomes 7/12, and we can see why that. But I think people are more tempted to add the denominators and numerators in this situation. But it's 6/8. So that's a whole number times a fraction. I want to say a little more about whole number times fraction. When you multiply a whole number times something like a fraction that has a 1 in the numerator, like half, that's the same thing. 8 times a half is the same thing as 8 divided by 2. And that's good to know. It's half of 8. Half times 8. That they could first work it out. 8 over 2 becomes 4. But I think to get the feel that like half of something is the same thing as dividing by 2, and 12 times a fourth of something is the same thing as dividing by 4, and 20 times a fifth is the same thing as 20 divided by 5. I think that's something that's worthwhile to explore and have people think about. Like in the case where there's a numerator of 1, that it's equivalent to just dividing by the denominator. A fifth of something is the same thing as dividing that number by 5. I think I should have maybe mentioned that before I started doing this. But the official like way of multiplying, sometimes people go like this. They call 20 over 1, so they can say multiply the numerators, multiply the denominators, and reduce the fraction. But I think it really is good for students to explore this idea that multiplying by 1/2 is the same thing as dividing by 2, and 1/4 is divided by 3, and so on. Now, when you want to do like 8 times 3/4, well, that's got a 3 on top. So, the official thing of multiply the numerator and then reduce the fraction. Improper fraction becomes 6. We could even go like this. I'm not saying that kids should do this, but I just want to show you as maybe adults. 1/4 times 3 is the same thing as 3/4, and 8 times a fourth is 2. So then this 3 on top turns it into 6 also. I say all this because eventually you have to multiply fractions by fractions. Like what is 2/3 of 3/4? It's interesting, when you multiply a fraction by something, it always gets smaller. Half of something is half. That's smaller. But when you multiply by 2/3, you end up with something a little bigger than half. So what is 2/3 of 3/4? Something that's a little less than 3/4. You could think of it as 3/4 times 2. It's a little less than 2/3 also. But luckily on this question, you could just multiply. 3 times 2 is 6. 3 times 4 is 12, and reduce that. You're even allowed, sometimes you have something like this, 2/4 times 3 over 3, and you can reduce the fractions like this by dividing numerator and denominator. Forgot to mention that over here. Remember back when I was making fractions, equivalent fractions, by multiplying like this? So reducing over here, 4 over 6, you sort of divide both by 2. The standard thing that we do is this. We just cross them both out and divide them both by 2. That's the notation for that. So we can reduce the fractions before I multiply. And you could, even in this question, this is more like, I don't think my daughter did this until like 5th or 6th grade, but that you'll get the same answer if you reduce like this 2 with this 4 have a common factor of 2, and this 3 and this 3 have a common factor of 3. It's not that obvious. Why am I allowed to reduce something from this fraction with something from this fraction? Well, it's pretty sophisticated, actually, why you can do that. I'm just going to say that since 2 times 3 is the same thing as 3 times 2, if I just switch them around, then you wouldn't, if we agree that these things are equal to each other and that this thing can definitely be reduced the regular way. But, we learn rules in math, like we just tell students, guess what? You're allowed to reduce, we say, across the time sign. Oh, I'm allowed to do that? Why am I allowed to do that? Well, it's good to know that you're allowed to, but it's also good to have some reason for why we're allowed to do that. Sort of an open question whether, if they're not ready to understand why they're allowed to do the trick, maybe we shouldn't even teach them the trick. Maybe they should just do it this way. So they reduce at the end. It's a little harder sometimes to reduce at the end because the numbers kind of got bigger, whereas in this, when the numbers are factored, when the numbers are separated already, it's easier to locate the common factors. Okay, going to finish out this video with division of fractions. So let's say I want to do 5 divided by 1/3. 5 divided by 2 is 2.5, which is less than 5. And 5 divided by 1 is 5, which is equal to 5. Well, 5 divided by 1/3 is actually going to be something bigger than 5, which is kind of confusing. We think about dividing. I'm splitting up, 5 cookies among what? Among 1/3 of a kid? It's hard to think of it that way. But you can actually do the 5 cookies, but not by splitting them among 1/3 of a child, but by doing the other division thing where we say, how many 1/3s fit inside of 5? If I split the cookies into thirds, how many thirds would I be able to give? And you could see it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 5 divided by 1/3 is 15. Because there are 15 thirds in 5, 3 in each one. And I think it's interesting to say, well, 5 divided by 1/3, if there's a 1 on top, is the same thing as 5 times the denominator. So you can do 2 divided by 1/6 is the same thing as 2 times 6, which is 12. If you want to draw out 2 cookies and cut out 6 from each, you can say, oh, well, there's 6 here, that's 6 times 2, which is 12. So the first sort of multiplication division rule would be that in the case where you're dividing a whole number by a fraction that happens to have a 1 in the numerator, it's the same thing as multiplying by 3. But what about 5 divided by 2/3? Well, this is kind of tricky. I just want to say a little something about this just to justify. 20 divided by 2 is 10. But if I divide by 4 instead of 2, it's going to be a smaller answer. It ends up being 5. So when I multiply this number by 2, this answer ends up getting divided by 2. try that with like 30 divided by 6 is 5, and 30 divided by 3, divided by 2, make that is 15. So when I divide by something that's like a third as small, my answer gets 3 times as big, because if I take the 30 and see how many 6's fit inside of it, I can get 3 times as many if I cut the thing into pieces that are 1/3 the size. Pretty sophisticated. Anyway, the reason I'm telling you this is because 5 divided by 2/3 is going to be kind of like, remember how 5 divided by 1/3 was 15? So, maybe I shouldn't use 5. Let me instead compare 6 divided by 1/3 versus 6 divided by 2/3. 6 divided by 1/3 is 18. Here's 1, 2, 3, 4, 5, 6. Here's, they're all split into thirds. And we can actually count. There are 18 of these here. Well, 6 divided by 2/3 is a little trickier. Here's my 6 again from up here. But if I wonder how many 2/3 there are, I'll take like 2/3 here. Here's another 2/3 and a third one and a fourth one and a fifth one and a sixth one. And the 7th one is going to be these 2 guys. And the 8th one is going to be these 2 guys. And the 9th one is going to be these 2 guys. So the answer should be 9, just by drawing it out. But officially, we can see that what ends up happening is we get the same answer we get with 6 divided by 1/3 is 18, but because there's a 2 up here, we end up dividing the 18 by 2, because this thing has gotten twice as big, so I can only get half as many as I would have gotten if there was a 1 up here. Very confusing, ends up with 9. And here's where I'm saying this all so I can tell you what the official trick is that they learned, and this might give you some memories, that you can divide by a fraction by multiplying by what they call the reciprocal. And it does get you the right answer. But the reason it works is because 6 divided by 1/3 would be 6 times 3. But 6 divided by 2/3 is smaller than 6 divided by 1/3 because the pieces are twice as big, so that's where the divided by 2 comes from. So we finished today with one of the most famous rules of all, dividing by a fraction. Dividing by a fraction is the same thing as we say multiplying by the reciprocal. Students, you don't have to fully understand that rule to use the rule. And I think it's okay if you don't really understand it that well. I think it's good to do this example, 6 divided by 1/3 versus 6 divided by 2/3, and the relationship between those two questions. But for sure, that rule of flip the thing you're dividing by and multiply is perfectly fine. And as an added bonus, it even works for fraction divided by fraction, which would be really difficult to draw out a picture of this. I've seen some Common Core examples where they try to draw this guy out. I don't believe in drawing this out. My belief is that you show dividing by a fraction with a 1 on top gets you multiplying. If there's this answer, it's like multiplying and then dividing by that number. And then we just have our rule that says flip the other fraction and multiply. Could even go further there. Okay, well that was a lot about fractions. But that's for 15 minutes. Students start learning about fractions in second grade, formally, or third grade, and they do it fourth grade and fifth grade, and people really struggle with them. So this video will take care of fractions all the way through sixth grade. And I just wanted to show you just some of my thoughts, especially thoughts about division, but wanted to let you know that I do believe that pizza, circles with pizza is probably still the best way. Number line, I'm not that crazy about, except for like measurement. I do like that, but the idea that the fundamental idea of a fraction is that it's a point on a number line between 0 and 1, I think that's too sophisticated for students. I think pizza is perfectly fine. And remember, small children, babies practically, the idea you only ate half, that idea of half is really still the starting point. We did not do decimals. That would be a lot. Part 5, decimals. Thank you.